So we're now ready to go explore in more detail Java atomic classes and operations. And we'll see that these are used to provide concurrent programs with so-called lock-free, thread-safe mechanisms to read from and write to single variables. And that's the key essence here, single variables. When we talk later about other kinds of synchronizers, you'll see how they build on these mechanisms in order to give you a broader scope of synchronization. And of course, you'll see one of my favorite things to do for all the examples we talk about is to discuss human known uses of these synchronizers. And I think you can already guess the human known use we're going to use because I've mentioned it before. So there's a bunch of different types of atomic actions on objects. I've given you a summary before. So atomic variables, which provide you lock-free and thread-safe operations on single variables, are one of the things we'll talk about. And for example, the class atomic long, which is very similar to atomic Boolean and atomic reference, is a good example that will encapsulate the underlying and unsafe compare and swap operations we mentioned before that are really the purview of the internal developers of the Java class library, and then expose them up to application developers through a nice, easy to understand Java interface. There's also another class that's an example of this called long adder, which sounds like a snake, if you think about it. And it allows multiple threads to update a common sum efficiently if you have high contention. We're not really going to focus much on long adder in this course at all, but be aware that it exists, and it does come in handy for things. For example, hit counters in a multi-threaded web server could use long adder, but we won't spend a lot of time dwelling on that. What I'm going to do first is kind of talk about how atomic operations in Java are implemented in hardware with some support provided by the higher layer operating system and Java virtual machine or Java execution environment capabilities. And you can learn more about the hardware operations if you take a look at the link at the bottom of the slide. So let's start off first by talking about perhaps the most important low-level atomic operation, which is compare and swap, or CAS. And you can see here that the definition of compare and swap is to atomically compare the current contents of a memory location to a given value. And if and only if that comparison succeeds, in other words, they're the same, then you'll atomically modify the contents of that memory location to a given value, a given new value, and return the old value. So the actual semantics are very simple. In fact, they're almost laughably simple. But it's interesting to take a quick look and see how this could be implemented. Now, keep in mind, what I'm about to show you is actually not how it's implemented in practice, because this is implemented in hardware. But what I'm going to show you is logically what it's doing. So the first thing it's doing is it's doing the compare and swap operation atomically. So you can imagine there's some kind of magic mechanism that's part of the operating system or the hardware, probably the hardware, that will atomically do something. So you can think about this as kind of like, some magical mechanism like start atomic, as if that was something that would be something that the hardware would do. It would then have some instructions followed by end atomic. So you can sort of think about this logically as a synchronized statement, but it's not a synchronized statement. It's the hardware equivalent of a synchronized statement. So everything between start atomic and end atomic will run atomically, and the hardware guarantees that. What happens next is we take a snapshot of the current value at a given location. So imagine for a moment that this is C or C++. So we've got a pointer to some memory location that's non-null. We dereference that location, get the old value, and stash it into a local variable. And then we check if the old value equals the expected value. So if you look at the compare and swap method, you'll see that the second parameter is called expected. If the old value equals the expected value, if and only if that's the case, then we atomically update the memory location with the third parameter to the compare and swap method, namely the updated parameter. And of course, all this is taking place atomically. So what we're doing there is we're saying, if the existing value at a location equals what we expect, set that value to the new value and return the existing value. So, or the original value, the old value. So those are the semantics. Again, very, very, very simple if you think about it. Now, once you have those semantics, then you can implement a bunch of other higher level things. Again, here's kind of the lock mechanism that we talked about before. So let's imagine we have a lock method, or a lock function in this case, that takes in a pointer to some location in memory. And it will then call that compare and swap operation, which again will be done in hardware probably with a little C or C++ facade to access it. And we say while compare and swap, and we pass in the memory location, we pass in the value 0 as the expected value, and we pass in the value 1 as the updated value. And what we're saying here is while the value doesn't change to 1, keep looping. So in other words, what that's saying is if it was the case that the current value at that location is going to be non-zero, in other words, it's not the second parameter, then just keep spinning. The moment it becomes 0, which means unlocked or available, then compare and swap will atomically set the value to 1. At that point, it will go ahead and return the old value, which will be 0. So at that point, the loop will stop because we now have atomically set a 0 value to 1. As long as it keeps returning 1, which means in use, we keep looping. And the key thing to note here is that compare and swap must only be called once per lock attempt. And this is where you get yourself into trouble when you don't quite understand how ridiculously simple this abstraction is. And you'll run into this when you start doing assignment 1B. So you can only call this thing once per lock attempt. And it's meant to be a single atomic operation, which either works or doesn't. And it's guaranteed by the hardware. So again, you pass in the memory location, you pass 0, saying that's what I want it to be. If it is 0, set it to 1, and keep spinning as long as the current value is 1, meaning the old value is locked. Here's the unlock, twin or sibling to this whole thing, or inverse, I guess is a better word. Unlock takes the memory location and then atomically sets its value back to 0. So again, that's an atomic operation. That'll make it unlocked. So when someone unlocks it, it sets it back to 0, such that anybody spinning will then detect it is now 0, and they'll be able to atomically set it to 1. There are other primitives that provide much the same mechanism but aren't quite as flexible. The other classic example is called test and set. And this has been around probably even longer than compare and swap. And it basically atomically modifies the contents of a memory location and returns its old value. But the way this works is it'll read the value of the memory location and it'll set it to 1, and then it'll return the old value. And so you can use this again to see whether something has changed or not. So notice we start out by reading the old value, and then we go ahead and we'll return what the old value was. And once again, you can use this kind of the same way. You can implement lock and unlock in very similar manner. It just is going to be a little different, where you're going to call the test and set with just the lock location. And so you can't give it arbitrary values. It only goes from 0 to 1. Whereas with compare and swap, as we'll see, you can be a bit more flexible. So compare and swap provides a more general solution than test and set. And that's because you can set its value to something other than 1 or 0. Whereas with test and set, you are stuck with 1 or 0, which is fine for a lot of things. But as you'll see, the fact that we can have arbitrary values be used with compare and swap give us an advantage to build more powerful atomic classes that leverage its features to do things efficiently. So again, just a quick recap, the human known use would be the Star Trek transporter beam. If you don't know what a transporter beam is, take a look at the link below. It basically converts a person or an object into energy and then beams them to some destination where they're converted back into matter. And again, this is one of those things like time travel that we're always looking forward to having and never quite get there. Back in the day when people actually drove to work, we wanted transporter beams to avoid traffic congestion. Nowadays, nobody's driving to work, so I guess the need for a transporter beam has been reduced. Clearly, if this process doesn't happen atomically, even though it's science fiction, horrible things will occur. And if you take a look at this link, it actually talks about transporter accidents that have occurred on the Star Trek show. The other human known use is apparition in the Harry Potter sequence, where you can basically disapparate and go from one place to another. And if you are not careful, you can splinch. And that actually happens to Ron Weasley in one of the books. I forget which one it is. It might be, I don't know, Order of the Phoenix or something like that, where they're learning to apparate and disapparate. Okay, so that's the end of the overview of Java's atomic classes and operations.